Welcome everybody. Welcome to tonight's SLAC public lecture. It's great you could all be here on such a cold night. Tear yourself away from your holiday shopping and everything. And today we're very fortunate to have Greg Loew as our speaker, and he's going to tell us about, as you can see here, big machines and big science, 80 years of accelerators at Stanford. And Greg's really the perfect person to give this talk because he's seen over half of this history personally, and he's gone to trouble to research the rest of it for you. Before we get started, let me just tell you that in case of emergency, we have these exits located over here. The oxygen bags will drop from the ceiling and all that stuff. So, so then Greg's a native of Paris, France. He grew up in Paris and also spent some time in Argentina during World War II. And after the war, he returned to Paris and studied at the University of Paris, receiving his, and I'm going to butcher this, licence et sciences in physics and chemistry in 1952. He says he'd always planned to study in the U.S., and he went to the right state, but the southern part of it initially, to Caltech, where he earned his master's in electrical engineering. Then he came up the coast to Stanford, receiving his PhD here in 1958. And at that point, Greg became one of the very first employees of the Stanford Linear Accelerator Center, starting with the time of his PhD half a century ago. And during his tenure here, he's worked on basically every machine that has been built here at SLAC. He also led the microwave engineering group, the accelerator physics department, and was deputy director of the technical division for 2 decades. He served as deputy director of the lab from 2001 to 2005. And he also has a high profile nationally and internationally. For example, he chaired a committee that reviewed the kind of technology you need to build a future electron-positron linear collider. So since Greg's been around at SLAC from its very inception, he's, again, the perfect person to tell us all about the history of accelerating electrons here on the peninsula. So would you give him a warm hand?
Thank you very much, Lance. So tonight my purpose is to tell you a story. It's the story of a very long adventure, as you just heard. I lived through about half of it. And this adventure starts in 1928 when William W. Hansen, who was a brilliant 19-year-old senior at Stanford, joined the physics department to do research. By the way, he came to the university when he was 15. The adventure I'm going to talk about moves through 80 years of machines and discoveries at Stanford and at SLAC. And my talk is going to cover 2 separate types of physics. Physics of particles and physics with photons. Both of them done using accelerators. Now, to make it understandable, I will have to summarize and skip over quite a number of details. And I have to tell you that I feel a little bit like Phileas Fogg in the 80 Days Around the World. I'm not sure I'm going to make it to the end. Anyway, I'm going to give it a try. So we start with X-rays at Stanford. And at the time, scientists in the physics department were using X-rays to examine the behavior of atoms. And atoms at that time were already known to have a nucleus containing protons and neutrons and electrons going around it. There were simple atoms that, like hydrogen, that had only 1 proton, and much more complicated atoms like uranium had 238 electrons around it. Anyway, the X-rays they were using were produced by electrons accelerated in a vacuum tube. Here's this vacuum tube, and it was connected to a 200 kilovolt DC power supply. So if you threw the switch here, then you applied a voltage of 200 kilovolts between this plate here and this other plate here. There was a heater behind this plate that heated the one on the left, and it got so red hot that it would emit electrons, and the electrons would be attracted by the positive charge on the other plate called an anode. It's very much like a TV tube, and the collision here of the electrons with the metal would put out X-rays, and the X-rays came out in all directions. And machines that are used today for your teeth or for your body, and when you go to the doctor, they're still pretty much like that. And the reason you have to wear an apron when you go there is because you don't want to get all this X-ray radiation on your body where you don't need to see it. Anyway, now we go from X-rays to electrons. And by 1929, Hansen joined this X-ray research group that was using this machine, and he soon was working on his PhD thesis with one of these machines, graduating in 1932. By 1934, after a year at MIT and Michigan, as a postdoc, he was invited back to Stanford to become an assistant professor at 25. That was almost unheard of at that age, at that time. The physics department wanted to expand this nuclear research with X-rays, but Hansen soon realized that the way that he thought it should be done, the way of the future, was to do it with high-energy electrons as probes of matter instead of X-rays. But the question was, how could this be done? And so I should go back and tell you a little bit about how do particles, how do electrons, or any charged particle for that matter, gain energy from anything. So here's the same old device again. You have the same plate, you have the heater, you have the electron coming out. It's attracted when you throw the switch of this power supply to the positive, because negative is attracted by positive. And when the electrons come to this anode, you make a hole in the anode, and so the electrons come through and they get out, and that's basically the source of electrons. And that's the way it was done, and it was pretty simple. Now, I want to define a few terms so you understand the terms I'm going to use in the rest of my talk. And so I want to tell you about how the kinetic energy of these electrons that are coming along here is measured. And it's the product just of the charge of the electron, which is a very important number in physics, multiplied by the voltage that you apply across these two plates. So for example, if you put 1 volt across the plates, you would get an energy in a unit called electron volts, a very small unit of energy. You would get, this electron would have an energy, a kinetic energy of 1 electron volt. If, on the other hand, you were able to put 1,000,000 volts across these two plates, you would get 1 MeV, mega electron volt. And if you could get 1 billion volts, then you would get 1 GeV, 1 giga electron volts. So these are units that are going to come back through my talk, so that's why I wanted to define them. But of course, the problem confronting Hansen and his colleagues at that time was that obtaining these high voltages was very difficult and extremely expensive. They didn't know how to do that. So a new idea was needed. And what was that idea? Well, it turns out that after much thinking, Hansen came up with the idea of a copper microwave resonator, which is shown here. And what was it? It was just a cavity, and what you see here, the outline, is the cross-section of this cavity. It could be a pill box, or it could be a rectangular box. And it was excited by a microwave generator. And you squirted the electrons in from one side. And if you did it at the right time, when the oscillation was taking place in such a way that the resonator would deposit positive charges on its side, the electrons would be attracted, would come through, and they would come out with higher energy. Now, the advantage of the microwave generator was that you could leave it on for a while, and the fields would build up, so you could get a higher voltage across the two sides, the two plates. There was only one problem there, that after 1/2 cycle, the fields, or the voltage, if you like, or the charges, would reverse because the thing was going back and forth. And so if you injected the electron at this time, it would go in this direction. It would see the negative charge here. It would be repelled and would go backwards. That was no good. Okay? Well, don't conclude that it was no good, because I'll show you in a minute that this idea could be used for something else. But for acceleration, it was no good. So what you had to do, actually, is to make sure that when you inserted the electrons here, the field, or the voltage, was in this direction and the charges were on this side. Okay, so Hansen put a model together of this idea, and pretty soon he had a square cavity, which he called a rhombatron, which he completed in 1937. And the reason he called it the rhombatron was because it was like a rumba dancing inside. The fields were going back and forth, or the voltage was going back and forth, dancing inside. And that dance was already very popular, so that's the way he called it. And it was driven by two vacuum tubes up there. For those of you who are a little older, you would recognize these tubes were triodes, but nowadays we only work with transistors, so we don't know about triodes anymore. But anyway, there was a little hole there, and if he had wanted to do that, he could have driven an electron beam through there, and maybe the electrons would have picked up a little energy. But there was another problem. It was a great invention, but it was totally insufficient. So why was it insufficient? Well, the tubes were not powerful enough to produce the desired electric voltage inside the cavity. And so, by chance, fortuitously, at that time, two of his friends, Russell and Sigurd Varian, who later on founded the Varian Associates, appeared on the scene. Russell was actually a friend of Hansen's, and he had roomed with Hansen at Stanford as a senior, and they were interested in something completely different. They were not interested in accelerators. They were interested in flying, because Sigurd Varian had gone to Mexico with his little plane many times, and he didn't like to land there at night or without having any navigational aid. So they worked together, and eventually actually very soon afterwards, they invented the klystron, which was a new microwave generator. It was also invented in 1937. Now, how does this klystron work? Well, it's shown here, and basically they used the idea that Hansen had already had with the little pillboxes, in this case they were now round, which were connected to each other. By the way, the word klystron comes from the Greek klys, which means wave breaking on the beach, and tron, which comes from the word electron. They combined it together, so that was why they called it a klystron. And the way it worked was that you would squirt an electron beam here, and as I said a few minutes ago, you would excite this cavity. It would bunch the electrons a little bit because the fields were going back and forth, then it would go into the second cavity, and it would generate more microwave. And you could do this with greater and greater power if you were smart, but at that time they just had a few milliwatts coming out of this. Well, these guys were pretty ambitious, and so instead of building an accelerator, they got a completely different idea, and they said, let's see if we can use this to do blind landing. So they built the klystron, which this time was working at 750 megahertz, a higher frequency, almost twice as much as the other one. Sorry, not twice as much. It was just 750 megahertz. And they built it here at Stanford. Here were the two Varian brothers, head of the department, another guy, and Hansen. And then they took this device to Boston, quite secretly actually. It was something that was not advertised at the time because it was already getting close to the war. And they put this device in this truck here. They connected the electrical power to this horn, and then they gave a little receiver to this plane, and they told the plane to fly 5 miles away. They turned on the klystron. The horn put out a beam, and they told the pilot to just come in without looking at anything, just fly into the beam. And that was a success. It was one of the first times that a plane had ever landed blindly this way. And it was kept pretty much under wraps, except that finally it leaked out, and this guy finally had his picture on the cover of Life magazine for doing this. Oh, it was quite interesting. Well, then the World War II came, and all these scientists went to the East Coast to work on defense. Hansen and the Varian brothers spent most of their time working on radar at the Sperry Corporation in Long Island. But Hansen had not forgotten his dream of accelerating electrons, and so after the war he came back to Stanford in 1945, and he was greatly encouraged by Fred Terman, who was then the Dean of Engineering, to work here, and he started his research again. Just showing this picture because some of you may have known this gentleman or seen him or heard about him. He is often considered not just the dean of engineering, which he was between 45 and 55, but he was also, he's considered now by many people as the father of Silicon Valley, because he brought so many young people here, started so many companies, and started this whole boom here. Anyway, by 1946, Hansen had figured out how he was going to accelerate electrons efficiently. And the way he figured it out now was going back to this cavity or this resonator I showed you before. He said, well, let me just line up several of these resonators side by side and just feed them from one end here and arrange things so that the microwave power would go in here through this hole, excite the next cavity, excite the next one, excite the next one, and shoot the electron through, and then the electron would pick up the energy not just of the first cavity, but all of them. So the more cavities you put there, the more energy the electron would pick up. For this, he enlisted the help of several graduate students and his colleague at Ginston, who had also been at Stanford and worked at Sperry during the war. And coincidentally, actually, without him knowing this, there were people in the UK who was doing the same work. There wasn't a communication like this today. There was no internet. There was nothing of that kind. And they actually beat Stanford to this idea, and they were they managed to accelerate electrons a few months before Stanford did. This came out later on. At the time it happened, they didn't know. Anyway, here is the first sketch that Hansen had drawn by one of his draftsmen, and it really shows all the components of a linear accelerator. A magnetron, at that time there was no klystron, pulsed by a pulsar here, would put out some microwave power. The microwave power would come into this pipe here, the same one that you just saw, which expanded. In a view here, it looks something like this. There was a gun, a pulsar for the gun. The gun would put out some electrons. The electrons would enter this pipe. They would see the microwaves, and they would be accelerated. The thing that's so amazing that this sketch dates back to 1946, and today most linear accelerators in the world look pretty much the same. There hasn't been that much of a change. As a result of this drawing and the work that came up in the year after that, an announcement was made by Hansen, which is probably the shortest paper that was ever written in the history of science. He wrote a paper to the agency and said, we have accelerated electrons. That was it, okay? That was enough. And this was actually happened on April 21st when you look back into the documents. Now, this is a huge success. Here you can see the man in front of his linear accelerator. The electrons came in on the side. This was the linear accelerator itself. This is another collimator or something. The klystron is not seen on the picture, or the magnetron is not seen on this picture, but the power came in this side, came in here, and then what was left over was dissipated and loaded. And the beam came out on this side here. The first beam he got out of this was about 6 MeV, 6 million electron volts. And this machine was called a Mark I linear accelerator. This accomplishment actually showed the superiority of Stanford over Cal forever. I mean, no big game could ever match this, because here was the accomplishment, okay? Here was Hansen with his 4 students carrying this machine on his back, and here was the opposition in Berkeley. They were trying to accelerate protons, and look what they had to do. They had to sit on the machine, okay? And actually, if you had a microscope or a telescope or whatever, and you look very carefully, those of you who have a good eye here would recognize this gentleman who was sitting on this machine here was Pief Panofsky, who's going to reappear in this talk in just a few minutes. Anyway, so Hansen really had much bigger ambitions. He didn't want to stop there. He didn't want to just have a little machine this big. He wanted to achieve a 1 billion volt or 1 GeV machine. He wanted to have a machine that was 100 meters long to accelerate electrons to bombard atoms. And the idea to probe the nuclei, the protons and the neutrons inside the nuclei, in a target was, the idea was to study the pattern of the electrons as it came out. And so here is a picture of the simple idea. Here's the accelerator. Here are the electrons coming out. Here's a target. the electrons hit the target. This time they make X-rays, but they make a lot of most of the electrons come out on the other side because they have high energy. And you look at this pattern, you try to figure out how this pattern corresponds to some theory to see what might be inside of these atoms, to see try to figure out the constitution of these atoms. Okay. Unfortunately, Hansen had a very tragic end, which you'll see in a minute. Armed with his success with the Mark I in late 1947, he applied for funds to the Office of Naval Research, which in those days was funding particle physics, and soon thereafter started construction of this machine, of this 100-meter machine, which was going to be called the Mark III. Now, a lot of developers would need it. They had to build klystrons and structures and modulators and vacuum systems and support systems and shielding and everything. And they did this. But tragically, in 1948, during the construction of the machine, Hansen became seriously ill. He'd already had some problems during the war, but he became very seriously ill. And in May of 1949, he died of lung disease. Probably, it's not known for sure, but probably because he had machined beryllium, which is an absolute no-no today, with his own hands, and he probably inhaled some of the beryllium. So that was a terrible loss. He was not even 40 years old. Luckily, his colleague at Ginston, who was his second in command, became director, and 3 years later, this Mark III machine that Hansen had started became a reality. So here is now Ed Ginston standing in front of the accelerator. You see the accelerator structures here. You see a waveguide coming here, and the klystrons, which had been built, cannot be seen on this picture. They're behind the cage here. As you can see from so far of all these people, they all wear ties. They're much more elegant, but that's the way they were. That's the way it was. Students wear ties, okay? Anyway. Now I want to just open a little parenthesis here and find out, justify our existence here, us people here. And that is, why do physicists always want bigger and bigger machines with bigger and higher energies? Is it just because we're so greedy or something, or have megalomania or whatever? No, it's not because of that. There are two ways of looking at this. One way is to think about accelerators as huge microscopes. And you know that when you have a microscope and you try to look at some little object with light, you can see objects that are of a certain size. But if you want to look at a DNA molecule, for example, you need higher energies. You need something like X-ray, maybe, or at least ultraviolet light. And these rays have more energies. Well, the same thing is true for particles. The more energy the particle has, the smaller objects it can look at. This is one reason. The other way of looking at this is that the physical world that we live in contains a whole spectrum of particles of ever-increasing masses. And because of Einstein's famous equation, E equal mc squared, if you want to make something that's very heavy, you need more energy. So to produce particles, we need electrons with correspondingly increasing energies, because the m goes up, the E has to go up as well. Okay, two particle physicists earned their fame on the Mark III accelerator. The first one was Robert Hofstadter, who's shown here, and he came from Princeton to Stanford in 1950, and he used the electrons, just like in the idea of the microscope, to study nuclei of a large number of atoms. He did encyclopedic work. And you can see from this one curve here that he tried to measure the charge density inside of nuclei of increasing mass. So he started with cobalt and indium, antimony, gold, bismuth, and so on. And for each of these materials in the target, he got a different curve. And he did this for so many different atoms that it became irresistible. In 1961, he got the Nobel Prize for this work. Anyway, the other guy, second one, was Wolfgang K.H. Pief-Panofsky, that many of you may have heard about. And he's shown here, young P. Panofsky. He came to Stanford from Berkeley, as you just saw. He was sitting on that pipe a few minutes ago. He came from there because of the loyalty oath controversy that took place there. Now, most of you don't know about this, but it's a complicated story. But what happened was that the University of California, during the McCarthy era, demanded that scientists who would work there would have to sign this oath to prove that they were neither communists nor, as Panofsky used to say, contaminated by communism. And so he didn't like the atmosphere this created, and that was Stanford's luck, because then he came to Stanford. He left the place in disgust, and he came over here. And he worked on this Mark III linear accelerator. He did meson studies. He became director of that lab. And soon he was known worldwide for his physics and also for the work he did in arms control. Now we're moving towards SLAC. Well, SLAC at that time was not called SLAC yet. It was called Project M for Monster, because it was assumed to be very big. Okay? So after 5 years, this Mark III accelerator was so successful as a machine and as a research tool that by 1956, Hofstadter, Panofsky, and their colleagues, Felix Bloch, by the way, was the inventor of the NMR, which is another famous thing. He got Nobel Prize for that, decided to set their sights even higher. And they came up with a design proposal for a possible 3-kilometer-long electron linear accelerator with an energy of 20 billion volts, so that's 20 GeV in this terminology that I used before. And as a result of that, the idea of SLAC was launched. Now, here is the proposal that was submitted to the AEC, the Atomic Energy Commission at the time, and in April of 1957. And when I came here to work here after I finished my degree, I was given that book. I still have it. It still has my name on there. And of course, I had to study it to figure out what these guys were going to do here. And it was not a very big book, about 80 pages. And it had there was a sketch in the book, which I put on the cover, of the site, which was going to be by the golf course over there. That's where we thought they thought they were going to build this machine. Well, the battle for the Atomic Energy Commission approval of Project M went on from 1957 to 1961. And a lot of questions arose. President Eisenhower approved the project, and the Congress didn't want to approve it, and the university had problems, and the physicists didn't know what was that machine, all kinds of people fighting. But nothing new, really. I mean, this is just like just 4 years. I mean, we approved $700 billion in a week now. Well, it took 4 years to approve this thing. Anyway, Congress eventually approved the project on September 15th, 1961, with a budget of $114 million for the current Sand Hill site where we're sitting right now. And that's, in today's money, is about $1.2 billion. It's questionable as 1.2, 1.3, whatever. Anyway, it's a lot of money for a physics device. So Wolfgang Panofsky, who just died last year at the age of 88, became our first director. And here you see him trying to convince the Board of Trustees at Stanford of the idea that we were doing this here. Well, he had incredible power of conviction with everybody from the Congress all the way to here. And so eventually on December 1961, the Stanford Board of Trustees named the project the Stanford Linear Accelerator Center, or SLAC, for the indefinite future. Now, you may have read in the papers recently that our name was recently changed to SLAC National Accelerator Lab. I won't go into this now. You can ask me the question afterwards. It's a shaggy dog story. You'd be here until 10 o'clock. Anyway, so let's go back to the idea of the electron linear accelerator, what it looked like. Now the idea was to have, pretty much like Hansen had done it, a modulator, a klystron, would put out a microwave energy. The energy would go into this pipe. This would create a traveling wave along here. Electrons would come out of a gun. They would come into this first cavity here, and they'd slowly get bunched, and they would come out. Now, The sketch here of this traveling wave is the wave of the voltage wave, if you like, that's traveling down here, that's produced by the microwave. And to pick up the maximum voltage, you had to put the electron bunches right on top. And this was called a disk-loaded structure. The interesting thing is that today, if you go to any hospital in the country and you look for cancer therapy machines, the same exact device is there embedded in a gantry. If you go to some industries where they're testing metals, you find a similar machine a little longer like that. And if you go to a physics lab like this one, you see a machine with many, many of these pipes. Now you ask, well, how long do you make this pipe? Well, the pipe is made out of copper. So what happens is that when you put the power in here, eventually, because the copper has some resistance, eventually this wave will become smaller and smaller. So if you keep on going with the same klystron, there'd be nothing to gain here. So you start all over again with a new klystron. And that's the compromise that you make between making it very short or making it extremely long. You make it about 10 feet long or something like that. So what was the machine going to look like? Well, here is the sketch of the machine. 2 stories, a lower part, the tunnel underground, and the part upstairs for the equipment that was going to drive the accelerator. And here I'm showing you what was upstairs and what was going to be put downstairs. The klystrons and everything that drove them was going to be in this gallery here, and the accelerator itself was going to be put down in this housing, this tunnel underneath. And in between, there was going to be a lot of earth shielding, because when the electrons went down the pipe here, they made some radiations and people couldn't live there. Okay? Couldn't be there, couldn't do any maintenance either. Well, Panofsky was a very early ecologist, and he picked the exact straight line for the accelerator that saved the most oak trees. And the way he did it is visible here. This is, by the way, is Sand Hill Road here. This is the accelerator. And if you look here at the straight line that he picked, because there's some choice here, he picked a line that would only cut a few trees here. Most of the other trees survived this construction. So it was a very nice thing he did at the time. This road here is Whiskey Hill Road. Portola Valley is there, and Hoover Tower is there. Anyway, construction started very quickly in 1963, and the housing underground made out of cement and concrete is seen here, this box, and then this was going to be covered with shielding, and then the other building was going to be put on top. The components of the disk-loaded waveguide were all made here. You see cylinders and you see disks, and these things were brazed together with this brazing material here to make a pipe like that. And the finished product here was a 10-foot linear accelerator sections, of which 960 had to be made. By the way, designing this structure here was my first job here. Anyway, then these 960 sections were installed inside the accelerator, mounted on an aluminum tube in which there was a laser beam that allowed you to align the whole accelerator. And then these pipes here were the ones that brought down the microwave power from the klystrons above. And the klystrons, there were 240 klystrons, which were built, most of them by industry. There was one type that was built here at Stanford. All the other ones were contracted out from industry. So on October 2nd, 1964, during the excavation of the end station at the end of the accelerator, the first major particle here was discovered. Here's the excavation at the end. Well, this is where all the experimental halls were being built. Here was the linear accelerator. The only thing was that this particle was not what you might expect. It turned out, for those of you who came through that door up there, that what was found here was this particle here, which was this strange animal called Paleoparadoxia, which is 14 million years old, which was found in its entirety in the excavation here. And the lady who is here is Dr. Panofsky's wife, Adele, who spent 30 years reconstructing this as a hobby. And here, what you see out there is a completely reconstructed animal. It's called Paleoparadoxia because it had fins, but it also walked. So it was walking on the ground, but also swam. Anyway, by spring of 1966, almost everything was ready to go. And Here is the site as it looked. The accelerator was pretty much finished. The end stations were built. The campus was pretty much done. This building here is the one where we're sitting right now. And the only thing that was missing, but it didn't bother us, was Highway 280. So you see, for those of you who think that 280s have been here forever, it hasn't. Anyway, so and on April 21st, the first 20 sectors out of 30 sectors in the machine were first used to accelerate the electron beam. It turned out to be a hard day's night in the control room because not everything worked immediately. And so here you see the people who were trying to turn this thing on, Professor Panofsky and some of my colleagues here, and yours truly here with a lot more hair than I have now. And we all looked very worried because the beam was stuck somewhere in the first kilometers, and we didn't know how to get it down the machine. Fortunately, after 2 or 3 hours, it was about 2 or 3 o'clock in the morning, the Beatles came in. You know, the Beatles were very important in those days. They still are today. And here they are, very happy, the same guys. Now, this was the artist's conception here who indeed, when the beam hit the sector 20, changed the atmosphere. So a month later, Panofsky made an announcement to the staff, and he showed in a letter that there was no computer, there were no computers here, so he announced this by a memo to everybody, showed this picture here, thanked everybody for the achievement, and this was the beam spot at the end of the machine, and this was the energy attained with some width of energy spectrum here. It's called a spectrum, and the energy was centered around 16 billion volts at that time. Now, particle physics started almost immediately, mostly with hydrogen targets. These hydrogen targets, as I mentioned before, are just protons. And the energy of the LINAC, as I just said, was about 16 GeV, but there was another thing we could do at the time already, and that was to produce positrons, which are the antiparticles of the electrons. And they have exactly the same properties, except they have the opposite charge. And they could be produced in the first kilometer of the machine, and because they couldn't go through the whole 3 kilometers, they only acquired 12 GeV along the length. Now, the first type of experiment that was done at the time was to use a hydrogen bubble chamber, which actually came from Berkeley. And here is a picture taken with this hydrogen bubble chamber. You just have to think about the electrons coming in here. This is about 1 meter in diameter here. The particles would come into the hydrogen and will do all kinds of interesting things. And depending on their charges and the fact that there was a magnetic field into the bubble chamber perpendicular to the picture, the particles would coil around in one direction depending on the charge or in the other direction. And the more energy they had, the bigger the radius of curvature was. There was a huge amount of research done with these, about something like 3 or 4 million pictures taken during the first years of SLAC. But there was a problem at that time. Things were getting very complicated. And why were they getting so complicated? Well, not just at SLAC, but in other labs in the world, over about 100 particles had been discovered. And nobody could imagine that if there were 100 particles, they could all be elementary. That was not simple enough. You couldn't really accept that. So the idea was that you had to have a simplifying concept of structure behind these 100 particles. Sure enough, in 1964, 2 theorists, Murray Gell-Mann and George Zweig, had separately come up with a very daring mathematical formulation. He was at Caltech, he was in Europe. Separately, they came up with pretty much the same idea. And this idea postulated just three subparticles of all these other ones, called, or most of these other ones, called U, D, and S quarks. And they're anti-quarks, so they were the quarks and the antiparticles, which in various combinations of 2 or 3 made up all the other observed particles. And another very weird thing was that they postulated, turned out correctly, that these particles, these quarks, had only 1/3 or 2/3 of the electron charge, plus or minus, but only 1/3 or 2/3. How that could happen, I still don't understand, but anyway, that's what they thought. And this was the, oh, and by the way, just to give you an example, if you think about a proton in their idea was made up of 2 U quarks and 1 D. So this one was 2/3 twice, that's 4/3. This one was minus 1/3. 4/3 minus minus 1/3 is 1, and that balanced the charge of the electron going around the nucleus of the hydrogen atom exactly. So this was the birth of what is now called the standard model of particle physics, which, by the way, still stands almost completely correctly today. And what did this look like? Well, it's represented in colors here. It looks a little bit like a Rubik's Cube, and what it contained was 3 families of particles. The quarks, these 2 quarks, but the third one, which I won't talk much about because it appeared in a slightly different way, which are these quarks which are held by a strong force inside the nucleus. Leptons, which are down here, which consist of electrons, and muons, which are the cousins, heavy cousins of the electrons, which feel the electromagnetic force and also responsible for another force called a weak force radioactivity, and their associated neutrinos, which are particles which move almost always at almost at the velocity of light, not completely. And then the third thing was along here, along the blue line here, an electromagnetic force carrier, because these forces have to be carried by something, and that was a photon. Well, that was the model. The question was, could these quarks, which was a figment of their imagination, actually be seen in any way? Could you actually check out the fact that they existed? Well, SLAC got involved in this very long story, and over 40 years, we've been involved in this series of discoveries having to do with these quarks, and we've reinvented ourselves many times along the way. But first, let's go back to the microscope analogy. Here is now the microscope again. The electrons are coming out. They hit a target. But now, because the energy is so much higher, you can produce a whole bunch of other particles. Not just the electrons, but other particles that have come along. And the first big experiment that used that idea was done in N Station A, which is one of the largest buildings here, with these so-called spectrometers, which are just called analyzers. And the way this worked was there was a target put here with hydrogen. The electron beam came from the linear accelerator from here, hit the target, and then these particles that came out, like I showed in the other picture, would be captured in these analyzers, and you could measure their energy. You could also, if you look at the size of a person here, you could also change the angle of this whole box and move it around so you could probe the way the particles came out. It was very reproducible. So both these huge structures could be moved along an angle. Okay, now these experiments turned out to be super successful. And between 1968 and 1972, the first evidence of the electrons scattered by the U and the D quark inside the proton and moving into the spectrometers, actually in a very complicated series of formulas, which the theorist sitting here can explain to you, verified that these things were real. They were not just figment of imagination. So this picture here now was established. And for this work, several years later, the 3 scientists who did this experiment, the co-discoverers, Taylor, Friedman, and Kendall, earned the Nobel Prize for this work in 1990. And here is Richard Taylor actually getting the prize from the King of Sweden for this work. Looked pretty happy, you would say. Anyway, meanwhile, back at the farm at Stanford, Burton Richter, who later on became our second director here, and his colleague from Princeton, Jerry O'Neill, had successfully built 2 little rings to store electrons. And Richter came up to SLAC with a new idea for the lab. And what you see here are these 2 little rings that he built at Stanford at the end of the Hansen machine there. There were 2 rings which stored electrons. You stored electrons in one direction, the other one in the other direction, and had them collide, and he did physics there. It didn't produce anything very new, but it inspired him greatly. And the reason it inspired him is he said, well, if I could do this with electrons, I should be able to do it with positrons and electrons, and I should be able to collide them head on. Well, So we went from the idea of the accelerator hitting a target to a new idea of building a ring here, which would store the electrons in one direction and the positron in the other direction. They would collide at one point, and things would come out, hopefully. It would be interesting. And this would be a colliding ring. So the way to do this was by having a channel of magnets all around that would keep the particles going in circles. Well, this was the birth of the electron-positron storage ring called SPEAR, where these experiments were carried out. And it turned out that the construction went very quickly. The ring was built. The idea was to store particles for several hours and then collide them. Operations started in 1972. And here is the ring. Still exists today, covered with shielding. The electrons, the positrons would come down from the linear accelerator back here and injected in both directions. They would collide in these two buildings. And a couple of years after this machine was turned on, major discovery was made. The discovery was that in 1974, when they scanned the energy of the two beams that were stored in there, slowly scanned them, they found that there was a huge resonance at 3.1, roughly 3.1 GeV. So one particle had half of the energy, the other had the other half. When they collided, they produced this 3.1 GeV, and nature gave them this resonance. And this was soon thereafter understood to be the manifestation of the fourth quark, so-called C-quark or charm quark, which Richter and his team discovered. And for this work, they very quickly afterwards, 2 years later, got the Nobel Prize for it. He got the Nobel Prize with another physicist from Brookhaven who discovered the same thing by a different technique. Anyway, the Rubik's Cube now is getting a little more complicated, and this C-quark had found its niche up here. So everything looked very simple, 4 and 1/4, and the rest was not quite understood yet. But then came a troublemaker here, and in 1975, 1976, another discovery was made on the same ring, and Martin Pearl, one of our other physicists, discovered the tau lepton, for which he got the Nobel Prize in 1995 and another prize early in 1982. Here he's shown with his discovery with the tau lepton coming out from the center point here, one going in this direction, the other one negative going in the other direction. And this now messed up things because now there was a third lepton. So there were now, and then soon thereafter they identified the fact that there was a neutrino associated with it. Now there were 6 guys sitting here, only 4 guys up there. That looked a little suspicious. Anyway. Meanwhile, in 1973, I'm going to run out of over time, by the way. I can see it already. Are you going to allow me, or are you going to kick me out? Okay, good. All right. All right. So in the meantime, another interesting byproduct had been found and began to be exploited, and that was synchrotron radiation. Synchrotron radiation is really ultraviolet or X-rays, which are emitted tangentially when beams are rotated around a circle. And what happens here, you have a magnet, and when the electron beam goes through this magnet, and it's told to go this way, it says, I don't like this, and it puts out some X-rays. And these X-rays were byproducts, but they turned out to be very useful. The people here who were here began to say, oh, this is something fantastic. So they built a little niche here, a little shack here, and they began to exploit this. Well, we're going to come back at the end of the talk to this business here because that's really the second subject of the talk. Meanwhile, after the success of SPEAR, a number of things happened here. Another storage ring was built. I won't talk about it. Some new klystrons were built here. There's actually a gentleman in the room here who was responsible for building this klystron. It was a much more powerful klystron, much bigger. And as a result of that, the energy of the linear accelerator could now go up to 50 GeV, which was more than twice the original energy of 20 GeV. That was pretty spectacular. And this possibly inspired Richter to come up with yet another idea. By that time, he was almost director already. And the idea was to say, well, I'd like to see if I could produce a particle that had been produced at CERN, which was called a Z particle, a very mysterious particle. I'd like to see if I could produce it on this campus. Certainly had a huge amount of real estate. Here we had only this small place. But this time he needed to collide electron and positron beams up to 50 GeV, because to produce 90 you need at least 45 plus 45, okay? So how do you do that? Well, you collide beams from two linear accelerators head on, and then hopefully you come up with this Z particle there. But unfortunately we only had one LINAC here, and so we had to live by our wits, and so came up with the idea of the Stanford Linear Collider called SLC. And the idea there was to put a kind of the head of a tennis racket at the end of the linear accelerator, accelerate the electrons and the positrons in the same machine, and then bend one beam this way, bend the other beam this way, and have them meet in at this experimental hall there at a focus. And for this required all kinds of new inventions, which I don't have time to go into, but we had to bring the beams down to micron size dimensions, and we had to bend the beams around, of course, and build a new detector. And so here you see the construction of this device. The arcs and the magnets, there were about 500 magnets almost that were built to bend the beams around. And then a detector was built. Here the detector is shown under construction by some of the chief physicists and engineers. And then you needed a big staff. As Hillary Clinton would say, it takes a village. But it takes a village to build and run a detector. And sure enough, here you see the village. So this was the picture of the staff that was running this detector by the time it was finished, climbing up and down here. The security people, the safety people today would not like this guy there. He was in a position, a slightly precarious position. But in those days, you didn't worry about that. Anyway, so by 1998, we're getting about 10 years away from now, the campus looked much more complicated. And here was this collider hall that you just saw. All these different beam lines and things going on, and the spear ring there, and then the accelerator, and so on. Anyway, the key results of this SLC were obtained between 1990 and 1998. And what happened then was that when you tuned the beams to about 91 GeV, pretty close to 90 GeV, under 100 GeV, you were able to produce these thousands of Z particles that had been produced at CERN. And you found out something which was pretty subtle, that the way these Z particles decayed was such that there could not be more than 3 neutrinos, because they decayed in neutrinos. If there had been more neutrinos, the decay would have looked different. So that was reassuring, because people were beginning to wonder, is this going to go on and on and on? We're going to end up with 100 particles again, trouble again. Okay, but this did not happen. The limit was, at least at that point, was 3. So in the meantime, the rest of the real estate had been occupied here, because Fermilab discovered the bottom and the top quark, which fit in here, and the CERN had discovered the Z and the W, which I talked about. This gluon particle, which keeps the particles together inside the nucleus, had also been shown to exist at DAISY. And so the cube was complete, and people pretty happy. Now, how many of you were here at the last talk? Oh, not very many people. Okay, well, so I unfortunately I have to talk a little bit about this. There was another idea that came up at around 1994 or so, and that was that physicists were really worried about the question of why is there so much matter in the universe and almost no antimatter. And so took another village of people to think about that idea and to build another project here. These are not the same people as before. Maybe a couple were there, but not total overlap. And what they did, they rebuilt this ring that was already in existence at the end, and they stored positrons and electrons in the rings with magnets that bent them around, and they did some very interesting physics, but this time they produced, with a total energy of 10.4 GeV, it was much lower, they produced B and anti-B pairs of, these are mesons. And they showed, they were trying to see whether the matter, namely the B, and the antimatter, the anti-B, would have the same lifetime. Well, they found out after 10 years that indeed they did not have the same lifetime, that there was a difference between the B and the anti-B. The difference was not big enough to explain the imbalance of matter in the universe, but it explained and completely verified the theories of two Japanese scientists who in 1972 had sort of predicted this. And for this prediction and the addition of these results that were obtained last year, these two Japanese physicists just got the Nobel Prize a few days ago. And although this machine stopped operation in April of 2008, the analysis is going to continue because I have a huge amount of data in the computer stored up, and so there will be a lot more PhD theses coming out of this work. So let's take one more look before we leave this beautiful box here. It looks complete, and it has one more discovery to be made, which will not be made at SLAC because we don't have a big enough accelerator, but it maybe will be made in Geneva, and that is the elusive Higgs particle that many of you may have heard about, and which is a particle which, if it really exists, will explain why all these particles have the masses they have. Unfortunately, the astrophysicists have come up and they've caught up with us, and they've screwed up this whole thing because they've shown to us now that this whole edifice here, unfortunately, is only 5% of the universe. At least that's what they claim. We sort of have to believe them. And so the rest of the stuff is presumably either dark matter or dark energy. So now we have job security for another 20 years. Because we don't know, we have no idea what that is. And meanwhile, actually, SLAC had already planned to go out into outer space to observe gamma rays, which might be connected with the dark energy, but maybe not. And the idea was to put a satellite out in space there. And the way this was done was to build a detector, which weighs about 3 tons, which is like a telescope, to look at gamma rays. It was put inside of a rocket, and on June 11th of this year, 2008, it went up into space, and it's up there now, and it's already giving very interesting results. That would probably be the subject of another lecture like this one in a few months from now when we have more results. Okay, now let me go back, and I still need about 5 or 7 minutes to close the loop on what happened with synchrotron radiation. It's not fair to shortchange these people because they did fantastic work, but that's the way it is. Okay. Life is not fair, Herman. Anyway, so SSRO started in 1973 and is still running strong today. And the spear ring, which I showed you, produces these X-rays and ultraviolet light. It's now gone through 3 incarnations. It's now called Spear 3. And we've come full circle back to 1928 because now these guys are really working with X-rays. But they're much, much better X-rays. And the reason they're much better is because I showed you before, they come out not out of this little tube that you get when you go to the doctor, but they come out of these rings. And if there's a magnet here, it puts out these X-rays or ultraviolet light. If you do better and you put a wiggle into this magnetic field of this magnet here, then you can increase the amount of light or X-rays that comes out of there. And if you do even better with a more sophisticated magnet called an undulator, you can focus this light to a very, very small spot, and you can increase the power enormously. Well, now if you go down to SSRL, which is over there, you see a huge set of beamlines that are coming out of this ring, and every little of these green boxes here is another one of these magnets that's squirting out photons, either ultraviolet or X-rays. I think they're mostly X-rays right now. And people sit here in these beamlines and they do experiments. Well, what do? Well, there are about 1,500 people coming every year here to use these machines, to use the photons, and they bring samples of various kinds. And what do? They do material science and solid state science, they do environmental science, they do archaeology. You may have heard a talk about archaeology here on this subject. They do medical and biological problems, and they also do a lot of crystallized protein spectroscopy. which is one of the last things that I want to talk about. So in order to do these experiments very quickly, they have automated everything. So they put all these little crystal samples in this dispenser here. They have built a robot arm. The robot arm picks up one of these samples at a time, turns around, puts it in this position here. The beam is turned on, and the detector sits here, takes a picture of this crystal, and then picks it up again, puts it back in here, brings up the next one. And this way, they don't have to go into the room very often, and you can look at hundreds and hundreds of samples almost automatically. So what's happened there? I'll just give you two examples to end my speech here. One example is the work by Roger Kornberg, which was the subject of another talk here about a year ago. And what he discovered was the RNA polymerase machine. This machine was discovered there. This is the very complicated molecule here, which is actually a little natural machine which exists inside the nucleus of our cells. And I'm not sure, but I think this is the DNA that's sitting there. And this machine goes in there, and when it has to do something, it unzips the double helix of the DNA, it copies the content of the code that's inside of this gene of the DNA, makes RNA out of it. The RNA becomes a messenger. It goes out into the outer part of the cell, uses the materials in the cell, and makes proteins. And these proteins, guess what are they? Us. That's what they are. Those are the proteins that make us. Now, the thing about these machines that's so amazing is that they know when they have to make a nose or an ear or a leg or a hand or whatever. That's another subject, but that's the way it's made. So for this subject, Roger Kornberg got the Nobel Prize 2 years ago. The other thing that was done, which was pretty amazing here, was when there was this anthrax scare, they brought the anthrax bacterium here, very carefully, of course, and they took pictures of that, and then they did an analysis with the SSRL beam, and they found the part of this anthrax bacterium that's the lethal part, called the lethal factor. And it's composed of several parts. The binding part, which binds to the cells of if we ingest it, and then the active site. And they found out that there is something happening in this active site here, whereby if this begins to act up, it cuts the enzyme, and then the enzyme being cut, it no longer can protect our immune system, and then basically we die. So the research now is to see how they can block the place here with various types of molecules to prevent this, because once you ingest this, you've had it unless this is blocked here. They have to block the entrance to this anthrax. Okay. There is finally one last invention that's being made here, which is just under construction right now, and that's the LCLS, linear coherent light source, or which is a FEL, which means free electron laser. It's not a laser in a little box. It's a free electron laser. And the way it was invented was on the basis of what we'd done with the linear collider, but this time just one LINAC was needed. If you put a series of magnets, of undulators at the end of this beam that's coming out, that's extremely small, you can get a huge number of X-rays or ultraviolet, but mostly X-rays, out of the source, and then you can do experiments with it. And the thing which is so amazing about the energy that comes out of there is that you have very, very short X-ray bursts now. And they're super intense. They're 9 or 10 orders of magnitude more intense than what anybody has made so far. And so the idea is that with these very, very short femtosecond, if you know what a femtosecond is, 10 to the minus, what is it, 15 seconds, you can actually take a picture of a chemical reaction, or you can watch a protein folding. And this is the type of physics that hasn't been done yet anywhere, but it's under construction now. Here is an undulator, and we have to make about 100 meters of this. They're being installed right now in this last part here of the linear accelerator, after the linear accelerator. And out of this will come these little huge bursts of energies of X-rays, and they will be measured in this hall here and then later on in this other hall. So this is the way SLAC is going to look a little differently from the way we've known it, but this is the way of the future. And if you look very carefully up there, very secretly, there's a little satellite flying, looking at us to see what we're doing. Anyway, so I've shown you all these different parts of the toolbox, the accelerator with the targets, the round machines, the storage rings, the way you can create synchrotron radiation, the way you can collide beams from two linear accelerators, the way you can make very short bursts of X-ray energies out of one linear accelerator followed by an array of undulators, the gamma ray thing, and this thing here I won't talk to you about because otherwise you won't come to one of the future lectures where we'll discuss this. So to conclude, I just want to acknowledge and thank a number of people here. Ingolf Lindau and Uwe Bergman, who work on SSRL, who gave me those beautiful pictures of those molecules. Also Herman Winnick here, who sent me another molecule. Gregory Stewart, who is from the SLAC Infomedia Solutions Department, who helped me with many of the illustrations. SLAC is an institution of wonderful people, all my colleagues who gave me this wonderful career here for 50 years. They were able to stand me here. It was amazing. I had the patience. And finally, I want to thank you because you are the taxpayers who paid for all of this. So thank you very much.
Greg, thank you for such a wonderful lecture and also for your 50 years of service to this institution. So we have time for a few questions. Any questions for Greg?
There's a question up there. I hope I can hear you. How do you make a klystron?
Positrons.
Oh, a positron. Oh, how do you make a positron? Well, there's a very interesting phenomenon which I didn't talk about, and that is that if an electron hits a piece of metal like tungsten, a very heavy, very dense material, it goes through this, and when it goes in there, it makes gamma rays, like the X-rays. Okay? And these X-rays and these gamma rays, in turn, many of them decay into two particles, one electron and one positron, if they have enough energy. And they do here. They have a huge amount of energy. So they can produce a lot of these so-called electron-positron pairs. So you arrange things downstream of that with this little wave thing that I showed you at the beginning with the accelerator. You change the phase. Since those charges are positive now, you can't put them on top of this wave, but you put them on the bottom of the wave, and you catch them this way. So these positrons are coming out of this piece of metal. They enter into this rest of the 2 kilometers of the accelerator. They get accelerated, and they come out at the other end. That's how you make them. How do you detect those positrons? Same way as the electrons. So all kinds of counters, all kinds of instruments. Actually, I didn't say that, but one of the very first experiments that was done here, there was one group that said, let's see if they're the same thing, except for the fact that they're positive instead of negative. So they did a very sophisticated experiment and with the spectrometers of those analyzers I showed you, and they put positrons in for a few days and put electrons in, did exactly the same experiment, except for the fact that the charge was opposite. They were identical. There was no difference. Yeah. No, I don't think it's going to be revived for this experiment of this B factory, which was doing this comparison of matter and antimatter. That's very unlikely because people have closed down now, and there's actually a possibility that some of the equipment that's used in there will go to Italy to build another machine in Italy. However, the tunnel itself has a tremendous potential for a bigger ring to also build a synchrotron radiation machine that will be much bigger. And so in the next administration, or maybe the second term, who knows, who knows, anyway, maybe that project, which is under design now, will become a reality. Yeah. Well, I'll tell you the truth, I don't know enough about this. What the people who gave me that slide explained to me is that once you understand that structure, I had another slide, but it's very complicated. Once you understand that lethal factor part of the head of that anthrax bacterium, then you can give these structures to drug companies, and they know how there is such a thing as a receptor in this system. And so if you can block this receptor, a lot of people have done huge amount of work on receptors. So if you can block that receptor with a chemical, then it wouldn't be able to attack you. But you know, that's work in progress. I don't know.
Let's take one more question in public.
Is there any rumors of the detection of the Higgs boson, and where would it fit on your
Okay, the rumors, there were some rumors that at Fermilab they might just find the Higgs boson, but they haven't, as far as I know, they haven't found it yet. And all hopes are now on the machine at CERN in Geneva, and that machine has had a setback because they started it in September or October, and then they had an accident, a helium accident, and so the machine is not going to come back on until about May of next year. So it's going to be probably a year. And the way the particle fits in there, it just fits in the theory, and you can ask these guys here, they know all about it. It's probably there, maybe it's not there. Either way, it's very important, because if it's not there, then it's just probably as interesting as if it is there. But it's been predicted by Higgs for over 20 years, 25 years now?
Like over 40 years.
40 years, okay.
1964.
Yeah, he's over 80 now, and he hopes to live as long as he has to see this particle actually discovered.
Okay, on that note, let's thank Greg again, and I'm sure he'll welcome more questions up here if you want.